making the presentation work, first of all. There we go. So I'm going to start with gas giants and a little bit about observations, but because I know a lot of you recognize a few of you, most of you will know a lot about this. I'll probably go quite fast through the observation side, but if it's something you're not familiar with, that's fine. Either ask a local expert or feel free to ask me afterwards. I'll talk a bit about only two concepts in gas giants. I'm just going to talk very briefly about the interaction between the dynamics and the chemistry and radiative transfer, and then a little bit about clouds. And then seeing how time goes, I'll then focus more on terrestrial exoplanets and tell you a bit about the work we've been doing there. So let's start with gas giants. As I've just said, hopefully we'll have time to come over and look at the type of terrestrial planets we model. So moving quite fast, and just to repeat, if there's something you don't understand, we can come back to it later, or you can come and talk to me. Essentially, detecting exoplanets is done in a whole bunch of ways, but one of the most significant, or the two most significant, are called the radial velocity method and transit. Radial velocity, you just have an orbiting planet essentially wobbling the star. You see the shift in the light, and therefore you get the mass. For a transit, and this is some beautiful data from the James Webb Space Telescope that many of you see now. This is for WASP 121b, working on this with a collaborator, Tom Evans. This is just the brightness of the star as the planet goes behind the star. So you use the brightness of the planet. And then as the planet goes in front of the star, it blocks some of the light. So very familiar for most people. This is an idea, it gives us an idea of the radius. And also, because the brightness of the system changes between this point where you're seeing the night side of the planet, and as it's rotating around, you're beginning to see the illuminated day side. This brightness difference can give us, we can then infer temperature gradients, which was done all the way back in 2008 by Heather Knutson for the first time. And if you understand climates of planets, temperature gradients, i.e. pressure gradients, are what kind of drives the circulation. The next technique that sort of gives us a bit more information is just during transit, we can measure the size of the planet as a function of wavelength and get an idea of composition. This is another recent example that I'll bring back up later. This is for a particular hot Jupiter called WASP 96b. And it's interesting because it doesn't seem to have as much obscuration from clouds and hazes as many of them do. So these are the JWST points in the green, an early reduction, and the black line is a model with some earlier HST and ground-based VLT observations. So again, this is just measuring the radius of the planet as a function of wavelength, but I'll come back to it shortly. Okay, great. So we can also do, oh, that's interesting. That's literally never happened before. Right, just going to make you dizzy and feel ill. All right, let's try again. So we can also go a little bit further, which actually at Exeter we haven't really engaged with a lot. This is high-res spectroscopy, and really on the modeling side, someone in the US is a massive expert on this, Emily Rauscher, and Michael Roman, who's now in the UK. They've worked with observers like Jane Birkby and Mattia Brogui, etc. And what you do is look at very high resolution measurements. And on the right is a plot of, it's actually ab initio, it's like modeling of all the different interactions of a water molecule. And you use the fact that you've got so many lines at high resolution to cross correlate and give you a detection of a species. And from that, this is just a raw CCD image of what it looks like. You see these curves due to things like the orbit of the planet, the Earth, the orbit of the planet. And using that accuracy, you get a residual, which gives you the velocity of the wind, which is pretty cool. And actually, Tom Loudon, who actually started working with us as a master's student years and years ago and has just got a job at the Met Office, which is sort of circular, he did this technique with Peter Wheatley in the UK and Warwick, where they did this at ingress, so when the planet comes into transit, and egress when it comes out, and you get a wind measurement for the two different hemispheres. The uncertainties are huge, but these type of techniques, as we get better and better, will give us the information we need to really constrain atmospheres in the future. So again, I know I'm going very fast through observations, but most of you know it. The final one that I'll pick out is emission. Now we can get this for transiting systems. You can remove the stellar flux and have a residual. It's normally done in a ratio between the stellar and the planetary flux, but probably more quality of data can come from directly imaged objects. And this is just an example of Sasha Hinckley, a good friend and colleague just over the corridor from me, who leads the ERS program on directly imaged planets. And these were the first JWST images released of young Jupiter-like planets, which are still very hot from their initial energy of gravitational collapse. So they're bright, they're sort of self-luminous in a sense. Direct imaging is going to be really important in the future, me and many others think, as we try to drive the technology down to smaller and cooler planets. So exciting to see this kind of stuff coming out. Right, so that was a quick whiz through. Basically, as a theorist, I get, with some uncertainties, of course, I can get, through various techniques, a mass, a radius, potentially a map of the temperature gradient, at least infer it. I can get compositions and possibly even some initial wind speeds to help me realize and constrain whether my models are giving me the right answer. So at Exeter, we work a lot with observations. David Singh used to be a member of Exeter University, and that was great. We could communicate directly. And now Sasha's joined a few years ago. But actually, the majority of our work is modeling. And we made a decision, or I made a decision many years ago, to stay very connected to the Earth model. And in our case, it's the UK Met Office model called the Unified Model. The reason I wanted to do that is because I also kind of cared about climate change on Earth. And rather than abandoning my career as an astrophysicist, which I was really excited about, I wanted to still work on that, but also try to contribute a little bit without getting in the way. So what we do is we use exactly the same model that the Met Office use. Now, at that time, that was fairly unique. Most models are somewhat divorced from their original kind of Earth-based progenitor. So that brings pain, because there are 500 or so researchers at the Met Office who are constantly submitting tickets and changes. We have to upgrade every 3 months. And in the past, that used to lead to a lot of breakages. And I've shared this story a couple of times during my visit to America, and it's getting easier every time I share it. But what I used to do in the early days when it was just me is whenever I got a new version of the code, I would run it as just a ball of gas doing nothing. And one time I did that and it started bouncing. What's going on? And it took me, I don't know, somewhere between 1 and 2 months to find the offending line of code, which said it set the top boundary pressure automatically to the pressure relevant for Earth. And it had a comment underneath it that said this should be done properly. That hurt. Now that we've come a long way from that. Now the Met Office run a daily suite of tests for Earth prediction stuff, but I've managed to squeeze in some exoplanet tests as well. And actually, working with Thomas and the wonderful set of benchmarks that we've set up and he set up, we want to put those in as well. So anyone that comes to use the code, to have this daily set of tests. Now, if they change something to make the Earth climate prediction better, no one is going to stop that because my hot Jupiter doesn't work, but I get an email which tells me which ticket has broken it and what's happened, so we can fix it much easier. Right, I've probably labored that point, but the point is that this is everything I show you today is part of an operational weather and climate model, and it has led to what I wanted, which is significant knowledge transfer. We haven't revolutionized weather prediction at the Met Office, of course not, but several things that we've done, and particularly through cuisines, have highlighted small errors in physical algorithms that were being perhaps covered up by the complex parameterizations that we use. So that has improved the model in some way. Okay, right. But let's talk more. I'll slow down now. Let's talk more about the actual applications and the science that we're doing. So on the gas giant side, something that myself and many of the group are interested in is the interplay between the circulations, the rate of transfer, and the chemistry but of course, how that then shapes the observations. And similar to the approach in climate science that people like Isaac Held have pushed for many years, I enjoy and think it's valuable in creating hierarchies of models, from very simplified, idealized 0D or 1D models, all the way up to what we might call kitchen sink modeling with everything, all the bells and whistles. And the reason I am very interested in that is that we know that planetary climates are complicated. So on the one hand, you can pretend that you're really clever and that you just know all the physics and chemistry, and you put it in and you press go and you get the answer. First of all, you wouldn't understand that answer. Secondly, turns out we're not as clever as we think we are, so we never put everything that needs to be in. On the other hand, you might run a very simple model and it matches the observations and say, hey, cool, hot Jupiters are simple. But if you've worked on climates for any point of time, you know that you can get the line to go through the dots for entirely the wrong reasons, actually, and make some bad inferences. So what I think we need as a community is this hierarchy of models where we compare simple, complete, and through that, we gradually actually learn about the physics that's going on in hot Jupiters. Now, what we've done here is sort of on the complex end, I would say, but still trying to strip parts out. So Maria Zamyatina has been leading a lot of work on no clouds, no condensates, no aerosols, which actually we know are there, right? So we know we're wrong by not having them in, but can we take them out and can we look at just how the gas phase chemistry evolves with the circulation? Now, Duncan Christie is now at Heidelberg. I'll talk about his work where he's then put the clouds in. And what does that do? So starting with well, let's call it the clear sky. This is something I bet many of you are very familiar with. It's a very simple concept, something the late awesome Adam Showman was so good at, thinking about a simple physical concept and how it might play out in different scenarios. This is a plot of mole fraction. So if you're not familiar with that, it's just the amount of stuff, and then pressure. So low in the atmosphere, deep in the atmosphere up here is much higher. And for different species, this is a simple 1D calculation. The dashed lines are using local thermal chemical equilibrium. So the chemistry is just determined by temperature, pressure, and elemental abundances. And now the solid lines are if we allow the material to move and we give the chemical reactions timescales, which are the best timescales we currently have, which often aren't ideal, but we have some very well, others not so good. And what you see is just that at some pressure, below this, everything looks the same. And that's simply because the pressure and temperature are high. The chemistry in this case is fast. So the analogy I like using, I use it a lot, is you've got an oven and you're putting ice in the oven. If the oven is really, really hot, the ice melts quickly. But if we go higher in the atmosphere, then maybe we can shovel ice in quick enough that the oven doesn't melt it. So up here, the material is moving up faster for a given kind of vertical mixing, which is a combination of both diffusion and large scale flows. So separating those two out was a bit tricky, but we get some bulk mixture. What you get is an abundance in a solid line of a whole bunch of species, which are different to what you might assume in equilibrium. Now, if we go even higher, we start to get photochemical effects become really important. And here, it's not the mixing, it's the photon-driven chemistry, which is pushing it away from thermal equilibrium chemistry. So once we get up into these regions, these processes in certain planets might be more or less important. We don't know. What we can do is put in what we do know compared to the observations and try to unpick it. This, as many of you will probably know better than me, this quenching, as it's called, was shown in Jupiter in the late 70s. I think it's a Basrian name forgets, but in 1977, this was shown in Jupiter. So transmission spectroscopy, which I'll speak a lot about, it depends on the composition of your atmosphere and etc. But roughly speaking, we're kind of looking in this millibari region. So for this particular example in 1D, you can see that this is right where things to get a bit interesting. So if you were to assume equilibrium and calculate something like a ratio between carbon and oxygen, then things might be a bit strange because you're seeing things that shouldn't be there, or vice versa. There are things not there that you'd expect. So what Maria has done recently is to run the same model, but in 3D. This model has not a complete chemical network. It's about 300 or so reactions. I think it goes up to sort of C2 molecules. Olivier Vinot released one that goes even higher. We haven't done that yet, but I think we'll find the same kind of thing. And run that 3D model where the rate of transfer knows what the chemistry is doing, and it has the opacities as good as we know them. The chemistry happens, the wind moves things around. It traces about 100 different species. And these are those same kind of spaghetti plots, but for different planets. So we have a very cool object and then a much hotter object. These are kind of rough effective temperatures. Now we're concentrating here just on methane, and you've got dashed lines at equilibrium again, and solid line is the kinetics calculation. The different colors here are now different longitudes around the planet. So on the day side, the hot day side, or the cold night side. Now, one important part of these hot Jupiters is we think it's a good assumption that they're tidally locked. So they're so close to the parent star, the tides basically force them into a circularized, co-rotating orbit, not co-rotating, synchronized orbit. So the day side is always the same face, just like the moon and Earth. So here, you don't need to worry too much about these, but these are just charting differences really in the temperature, in the dashed lines in equilibrium. But you can see in these plots that the solid line is collapsed. There's one. It's actually one for low latitude and one for the equator. But for the moment, the key point to take home is that for very cold things, relatively speaking, 800 Kelvin, but for cold things, the mixing is kind of winning out over the chemistry. And these things are pretty homogeneous, complicated chemically, but fairly homogeneous in these simulations. Then if we look at the temperature increasing, we start to get this quenching effect where the chemistry is kind of collapsing onto a point, onto a value, whereas in equilibrium, it wouldn't be. And that quenching point, importantly, is kind of changing with temperature. It's going to higher pressures, and the behavior is getting more complex. Here we have lots of solid lines. Now, at some point, if you go even higher to ultra hot Jupiters, the chemistry is going very, very fast, and other things become important, like recombination and dissociation of hydrogen, etc., but which aren't in these particular models. Now, these models are not quantitatively predictive, in my opinion. If they were to be, then that would be weird. It's a bit like when your code compiles without getting any bugs. That's great, but also scary. So these aren't really quantitatively predictive at the moment. What we're trying to do is flesh out where this is occurring and how its behavior might change across the parameter space. And crucially, I think complexity is an opportunity here, because you might look at this and go, this is annoying. We can't assume equilibrium. But if this simple concept of chemistry has a time scale and winds move at a certain speed, that might, if we can understand it enough, actually tell us what's happening deeper in the atmosphere, if we can knit that story together. And if you do, so I haven't shown them here, we've done quite simple tracer experiments. And the mixing in most cases is 3D. Material is being pulled in from the poles in an overturning circulation in the deep atmosphere, and then kind of lifted up vertically and then mixed zonally by a big coherent jet. These things are rotating very slowly, so they have a Jupiter-like jet, but much, much wider in latitude. Okay, so here's where transmission spectra are. You might expect this to have different kind of impacts. So what that led us to see is that it might not be HD 189 because it's sensitive to how we create the numerical algorithms, but we think in terms of the observations, there's like a sweet spot. Too cold, chemistry is a bit too slow. Too hot, chemistry is super fast. But in the middle somewhere, there's a crossover between the advective velocity, the flow, and the chemistry. And here's 189 in our simulations where the dashed and solid lines, kinetics and equilibrium, look different. And that's now bearing fruit in the JWST area. We've already seen impact outcomes of photochemistry. There's also confusion for a while, at least, about where the methane is. And these are disequilibrium. These are non-equilibrium effects caused by vertical, horizontal mixing of photochemistry. So cool. Sounds fun. This is just a plot to show that they're actually 3D simulations. This is longitude and then South Pole, equator, North Pole of a planet. This is the equilibrium structure. So the methane abundance is just tracing temperature. And this is when the kinetics is turned on. Okay, now this also could have implications on phase curves. So phase curves are this thing I mentioned earlier, where as the orbit of the planet changes, you see temperature differences. And actually, this is leading to a different abundance of particular infrared important species like methane, which are going to change your relative balance. Now, some of these, you don't really need to read into this plot. This is just brightness as a function of orbit. And all the lines are kind of different models. We've kind of tried to include different things. And it could well be possible that some of these discrepancies are caused by disequilibrium chemistry. But final point, this is just JWST synthetic data for 189. And you just see the same thing. We have equilibrium and kinetics for 189, and it shows in emission and in transmission potential signals. Something else that complicates things is that we often make a simplifying assumption that emission at a given wavelength might come from some pressure. And of course, you need a rate transfer expert like you have here to tell you where those photons are coming from. These are contribution functions, so where the photons are coming from for infrared wavelengths with equilibrium at the bottom and kinetics at the top. And basically the point to take home is these are different. The photons are coming from different locations because of that mixing. And that means that you're getting different pressure surfaces around the planet. So just a little kind of cautionary note. This is in a paper which I hope will be submitted fairly soon, that Maria's finishing up. These are simulations where we've now started to play with the metallicity. So this is looking down at the pole. This is a solar metallicity model where she's looked at quenching at a particular pressure level and a particular species. And then this is the pressure level then, sorry, not at a particular pressure level, but for a particular species. And then this is the quenching then changing as you have a different metallicity, as the chemistry is changing, the opacity is changing, etc. So the key thing I think to take away from this first bit is that, that mixing, we think, affects the chemistry, and whether it is affecting quantitatively what we see or not is a question to pick apart and to compare models to observations and understand where that transition occurs. And Maria is the name to look for, Maria Zamyatina. She's leading this work. She knows way more about it than I do. We meet regularly and I try to keep up with her, but she's definitely leading it. And this is just an example of something she's working on at the moment. As I showed you earlier, it's the black line is the model. It matches the observations quite well. Note of caution. That should make me a bit worried because we know there's physics missing, right? But okay, it's doing an okay job. Over here, this is hazes and probably small particles, meaning that we depart. We could put them in and make it look good, but we wouldn't understand what's going on. So there's no point in doing that at the moment, although lots of people are doing great work on hazes. And Maria's just picking out different species to see how they contribute. So check an eye out soon for hopefully something will appear. Take home messages that there's a kind of sweet spot in this mixing, exactly where it lies, we're not sure. And it can affect the observations like transmission and particularly phase curves, which JWST is doing a surprising amount of. At least I was surprised by how many phase curves were given time in cycle 2. Okay. Now we add in some clouds. Now I'm overselling this by saying we add in some clouds. We don't take the chemical kinetics and add in clouds nice and consistently. That's really hard. We have used models in the past where we use the models pioneered by Christian Helling and Elsie Lee, which create nucleation particles, titanium dioxide, which is thermally quite stable in these conditions. Then you have heterogeneous evaporation and condensation onto the surface of dust of these grains, these cloud condensation nuclei. And that was great, but it's one of these models that's really cool and it includes loads of great stuff, but it's of course only the stuff that we know or we think we know. So they're useful, but the problem is the time scale for the physical, the settling and the evolution of those particles is really, really long. So those simulations that we run were useful and interesting, but they're not probably anywhere near equilibrium. So they were effectively far too cloudy not comparing them to real life, but comparing where the simulation should end up. So we still have that capability and we still run those models, but we then try to go to the other end of the problem and use like a phase equilibrium model. So if you're used to Earth climate or GCM modeling, you would call it a prognostic or a diagnostic scheme. So we have a prognostic scheme that actually evolves things in time, and we have a diagnostic scheme that says, what's our temperature, pressure, and chemistry? Should we have clouds? Puts the clouds there, they affect the rate of transfer. We go on a time step and we do the whole thing again. So neither of those are right, but hopefully by doing both of them, we start to understand. So I'm going to focus on the diagnostic stuff today. So the equilibrium model, this is just an intro plot just showing you species like manganese sulfate, corundum, and enstatite and phosphorite for simulations of hot Jupiters, just where they are. You can see a sort of hotspot shape, etc. But more interestingly, of late, and one of the reasons I was going to catch up with Diana Powell, but awesome news, she's had a baby, so she's not around at the moment. But we've been talking a lot about, and she's doing great work without me, I'm just sort of wanted to pick her brains. The limb asymmetry issue has been on my mind for a long time, but it was something that we couldn't do with Hubble. So what do I mean if you don't know what I mean? Well, if the star is over here, we have these two terminator regions where the light is going through that we do transmission, and we have material in a jet flowing around. Now, that's a preferential direction once you get to a certain depth. So you have one limb that has different thermal properties. It's a different temperature, but also critically from my mind, it has different vertical velocities. So on the left here, we have temperature between two simulations that include clouds or don't. And the point here is that the terminators would, the hotspot is the subsurface points in the middle, and we have terminators that would be kind of either side, and their temperature structures are different. Then on the right, we have the same plot. This is vertical velocity. So at this terminator and this terminator, you have very different vertical velocity profiles, and that's really, really important for cloud structures, what sort of particles you can loft, etc. Now, the bottom here is just playing around, doing some transmission spectra for different limbs and different clouds, etc. But the problem we always had with Hubble is you need to do lots of orbits to get the signal. With Webb, you can do potentially break apart the two limbs of the, it's not easy, but break apart the two limbs of the planet and start to look to asymmetries. And I think that is super important. Now, I've put 4D down here because, you know, we always like to go one step further, and we've been looking at variability. So this is the cloud structure as shown by the sort of what you might call OLR, the outgoing thermal flux, as a function of time. And it's a little bit of fun. We need to get there. Webb will give us access to variability, but modeling wise, we're a long way from hot Jupiters from being able to be anywhere near predictive of time variability. The key point, I think, from that sort of slide is, is to the 3D mixing is important, and that gives us sort of heterogeneities in a certain area of the parameter space, and that we think we might have limb asymmetries in clouds. And cloud condensation, etc., is easier to spot sometimes because they give big opacity sources. I think the way forward is then to try to combine these kind of detailed measurements with JWST of individual objects with kind of more population studies so we can really constrain the models. I'm going to finish this hot Jupiter bit with a stolen picture of the south pole of Jupiter, just so it looks pretty, because they are pretty amazing shots. But I want to sell something I've been selling to everyone, and I want to do it, but I want everyone to do it. So we have these hot Jupiters, which are super interesting, and we're beginning to get, so here's the star, here's a hot side with material flowing here, and then a cold side with stuff flowing through, and we have these terminators here and here, which are different. Now, at some pressure high in the atmosphere, the radiative transfer is so strong, the timescale is so short, you just have kind of diverging flow. Just everything runs away from the day side. As you go deeper and deeper, you start to set up these jets for various reasons. And what I think is super interesting is that by picking apart these limbs and this sort of day side and night side emission, what we're getting at is timescales. So if we could have a measurement of something here, which is photochemical and behaves differently in the dark than it does in the day, then we can look here and we could do that across a population, and we could actually get a constraint on things like ratios between the dynamical timescale and the chemical timescale. And if we know the star emission pretty well, then that will give us a really strong constraint. Now, if we do that for different species at different pressures, we're starting to get a really cool map of what's going on. So like, I'm trying to get loads of people to get interested in that. Timescales are key. Right. I'll talk a little bit just for 10 or so minutes about Earth-like planets or terrestrial planets in a moment, but I want to just share you a bit of hot off the press news. So we've been using the It's great. It's a beast. It's like 1.5 million lines of Fortran. It's just huge. But it's owned by the king, as I always tell everyone, because each piece of Fortran has crown copyright at the top, because it used to be part of the UK's Ministry of Defence. So if you email the Met Office and ask them, can I use your code for exoplanets or solar system planets? What they'll normally do, so they don't have to do paperwork, which is fair enough, is email me and say, oh, why don't you just use it through Nathan? So I have been able to collaborate with people and share our developments. Now, the rate of transfer is called Socrates. That's inside this 3D GCM. That's open source. So we could share that easily. So that's now used in the NASA model in Rocky 3D. It's now used in ExoFMS version, and it's Eric plays around with it in ExoCam, if you're familiar with exoplanet observations modeling as well. So that's great, but is much harder to share because it relies on our capacity to be able to share it in an IT sense. So everyone has to come through our servers and things, which is fine, but I have to fill out a whole bunch of paperwork. The Met Office have realized the power of open source. So their new model, which they're building at the moment, Elfric, is going to be completely open source once it's not crashing all the time. This is so cool. It's using a CubeSphere grid, which is not a new thing. All grids, you have GCM people telling you this grid's better than that grid. Like, the answer is they all have different problems and different advantages. But this is not the key part. The key part is it's being written in a platform agnostic way. So when you do the code for the science, you write the algorithms, and then it sort of gets rewritten for different platforms, which is great for me because I don't care so much about that stuff, CPU, GPU, whatever, just want it to run. And it's also from the ground up being built to be incredibly scalable. The point is they want to run convection permitting models for the entire planet. And I just need to convince them to let me to do that for an M-dwarf orbiting planet. Same thing, right? Convection permitting are used because you don't really ever get to the scale of convection, but you get close enough so that your solution of the Navier-Stokes equations kind of aliases what convection is doing anyway. So this is coming. Dennis has just done the tie things and submitted it to geoscientific model development. And also we managed to make a hot Jupiter run just recently. And yeah, literally I got this plot a little way before we left. And this isn't that we've been silly. This is just that the plotting tools haven't had the continents removed from them yet. So this is an output of a hot Jupiter simulation with this kind of characteristic temperature gradient. So hopefully soon that will be used, but we want to do mini Neptunes as well using Camembert, another one of the tests here. So conclusions are radiation dynamic chemistry, they interact. Isn't that cool? But more importantly, remember these three people: Duncan for clouds, Maria for chemistry, and Dennis for the terrestrial stuff. Okay, so is it okay if I take 5 or so more minutes? Yeah, you're cool. So I'll focus a bit on terrestrial planets, which is much more where, well, Tom is getting his fingers into everything these days, but this is where we originally sort of overlapped. So something that's been fascinating me and lots of other people, I'm sure, is 2 questions. What would the Earth look like without life? And if we re-rolled the dice, would we end up with life on Mars or Venus and not on Earth? Now, we know that Earth's climate and the life forms on it have been interacting for billions of years. Oh, I forgot about this. Sorry. This is just here. This is super cool. Danny set up the for Mars. This is just a simulation of the dust populations. Sorry, I forgot this was here. I did that last time as well. The dust distribution on Mars is hard to get right for a whole bunch of reasons. And the models that do it right are really good. But what they do is they sort of force the model much more. And which is fine. But what we're trying to do is do it from a very first principles approach that just includes how the dust is lifted and try to get it right. Now, we don't get it right, but we actually get it all right, get it pretty close. So that model's in production at the moment. But the thing we've been focusing on more is this life-climate interaction on Earth. And many of you will be familiar with this more than I was. I mean, I've only learned this stuff in the last few years, that throughout Earth's history, this is the oxygen abundance. You can see it's varied a lot. It was low, we think. I mean, there's big uncertainties on this, but we think it was very low. And then there was a great oxidation event, et cetera, et cetera. So maybe modern Earth is not the best proxy for potential biosignature there is. If you were to just look at Earth through time, you're actually going to spend most of your time seeing something like this, potentially with a biosphere made of methanogens. And other people realize this a lot earlier than I did. So we're trying to sort of incorporate that and understand that too. So we started getting interested in the Archean, and we use a sort of atmospheric simulation with all kind of funky bits and pieces. But the key bit is we've been trying to understand the methane, as that's intrinsically linked to these early life forms. Now, something we found was a redo in 3D of the 1D results of Colin, it was Byrne and Goldblatt, which is something which may not surprise. I spend most of my career now being surprised by things by people in the room who have known for decades. But I'm okay with that because it means I'm learning, so it's fine. So this is a result where we, at a given CO2, we change the methane concentration and we get warming. Okay, that made sense to me. Methane's a greenhouse gas, fine. But at some point, actually, we get cooling. And that's caused by the surface sort of decoupling in a sense. And the atmosphere absorbing so much methane now, it's actually caused by what that then does to the clouds, and the clouds emit and cool it. But why is this cool? Well, this is super interesting for M-dwarf orbiting planets because more of the information is in redder wavelengths. So this effect would be really amplified. And also haze is probably starting to form in and around here. So Martha, who's working a lot with Geronimo on some intercomparisons, is also putting haze into the 3D model and trying to understand what happens for the Archean Earth before moving on. That's been done before, but we're trying to sort of add in extra complexity, do it in 3D, maybe include dynamics as well. Now, as I said, understanding that for M-dwarfs is really key because of their relative emission being at longer wavelengths. So I'm going to skip this slide because this is kind of more for astro departments who might be less familiar with Earth-like planets. So this is just an overview. We talked about all this mixing on hot Jupiters, a similar kind of picture, but you have moist convection making everything more complicated. So we have a hot day side of one of these potentially Earth-like planets. It's very close to its cool M-dwarf star. And we have this big kind of congestus region. We have updrafts and convection, etc. So many of you will be very familiar with these and trying to model them. Our contribution has been trying to understand convection, which Dennis is an absolute whiz in. And this is a simulation we did a while back where we took a global simulation and then put a really high resolution box over the day side. And you just get sort of, better resolution. But what that means you can do is you can free yourself from the parameterization that you have of convection. Because with convection and things like that, we have a problem that we either have really, really good parameterizations, which are set by observations of Earth's convection, or we have really flexible ones, which are often wrong. So it's kind of trying to bracket the two. And actually, this result was interesting in that it said it didn't make a whole lot of difference, but it did make a bit. So that was quite interesting. And trying to sort of understand how these things work is Dennis is now doing this kind of stuff in Elfric, etc. The other thing I want to highlight is the work of Robbie Ridgway, who's just finished his PhD. We used the same chemical setup and approaches that we used for the hot Jupiters I described earlier, but now we included photochemistry. So if you're familiar with this, it's the Chapman cycle plus the NOx and HOX. So this is just everything that goes into destroying and creating ozone. And these are simulations here where we don't have a flaring star. And here we do all the photochemistry, we invect things around, but we have a star like an M-dwarf that's flaring with a characteristic energy and rate that you would expect. And this is just the amount of ozone in Dobson units. So you can see that distribution is very different. But if we look vertically, we actually form in these simulations, similar to work done by Howard Chen and Eric Wolf, a second ozone layer deeper in the atmosphere. Now, this is just looking at the flares. This is actually the ozone composition, the ozone concentration, but it's tracking flares basically. And I guess the key result we found is that if you have a flare, it sort of protects you from the next flare a little bit. So if you run the model without any previous flares, you get a lot of UV at the surface. If you have some flares and then hit it again, you get less. Now, this, just for fun, is the UV index on the surface of this simulated M-dwarf orbiting planet with Earth's modern atmosphere. So there's all sorts of assumptions. We're just kind of understanding mechanisms. But you can see, even in the best case scenario, this is like a value of 50, and the top of Everest, I think, is a value of 10. So you need a lot of titanium oxide to keep you safe, but that's okay. You know, life is interesting in many ways. So I think there's a lot more to unpick, and I'm really relaxed and excited about all sorts of JWST observations that show atmospheres or not, or anything, because I think there's a lot to understand about terrestrial planets orbiting M-dwarfs. Right, sorry that bit was kind of jumped in at the end. I'm going to skip this a little bit. This is more about ozone and how it interacts, because I'm conscious of time. I'm talking too long. The final bit I'll just show you is more idealized modeling, but which is interesting too. Arwen Nicholson is working with us on trying to couple simple life forms with an atmosphere model. So you just have a metabolism. Now, again, another thing which all the ecologists in the room, when I found out, have known this for decades, but as an astronomer, I didn't. If you couple a metabolism with some atmosphere and you have geochemical sort of reactions that recycle something like hydrogen, in the early Earth, we have methanogens taking in hydrogen, taking out and putting out methane. You don't really care about the precise details of their biology, because it's a bit like a bath with a tap on and the plug out. What matters, how full the bath gets, is how big the plug is and how big the tap is. So actually, it's the hydrogen out of volcanoes and out of the top of the Earth that matters over long timescales. You don't care about the exact details. But this is super cool, right? Because it means if we can look at different metabolisms, and we've focused on methanogens for different kind of so here we've got like death rate, how much ATP it costs to stay alive. And you can see there's pretty much a flat line in this plot, which is just showing biomass versus a biosignature. This is a good result, because it means maybe we don't have to know all the details of potential life elsewhere. We just need to know fluxes of stuff. And this is really interesting in the sense that these are limited by hydrogen. But what about a super Earth that's still got a whole bunch of hydrogen around? It's possibly limited by photons then, which we're good at calculating stuff about, or is possibly limited by CO2 or something. So I think this is loads of work to do, but it's super cool. And Arwen is the one, she's going to be back from maternity leave in about a month's time, who's leading that work. Right, sorry for whizzing through the observations if you weren't familiar with those, but please ask a local person to come to me. And I'll leave then just with the reason I'm here, which is talk to Thomas and others about how we can merge more and support this excellent effort, which is the EXO model intercomparisons through cuisines. Thanks for your time.
Awesome talk, Nathan. Thank you very much. So, do we have questions here and online? Yeah, Ravi?
Anything online you want to take that?
Not right now. Go ahead.
Okay. So yeah, really great. Grateful, like great. Great. So there are two questions I want to ask. One on the Arcane one. It's not a question. Comment and question that. So are you familiar with Jada Arney's work, the 2016 paper on the Arcane with the methane CO2 ratios? And how do your results compare with the case formation from?
Yeah, great question. Thank you, Ravi. So just for people online, because only this microphone's working, Ravi was asking me if we're familiar with Jada Arney's work, particularly in 2016. And yeah, maybe what I should have said is Jada's a co-author on that paper. So we've been using the models here. So at the moment, this first effort was to use Jada's treatment to create a prescribed haze and then apply that just as a static haze in 3D and see what it feeds back. And then the next step is then to evolve it dynamically, which Martha's working on at the moment, but she'll be doing that with Jada. So actually, I hope that you're all going to meet Martha at some point in the future, because I would like to send her over here and come and spend some time to work with people. Thank you.
The other question is on the art. You can go back to the slide on different planets with equilibrium and
Yes. Okay. Just get the right one. For some reason, the figures have disappeared. Oh, there they are. This one?
could you tell us what the stellar fluxes on these planets look like? Like how far away each planet is from this?
Yeah, okay. So the question, oh, sorry.
So I think there's a deeper motivation.
Okay. Yes, so the question was, what I've done here is maybe a bit lazily is just put kind of equilibrium temperatures or effective temperatures rather for the stars, but I haven't said anything about the stellar flux. So are they closer or further out? So my answer is, I don't know. I can't remember. So, but we have them in the paper. So their rotation rates are all based, they're all assumed to be tidally locked. And the chemistry is calculated given a spectrum of that star at the orbital radius we think it's at, but I haven't got the flux numbers instead.
Right. The reason I'm asking is that if they are incrementally closer to the star, this probably could explain why, just to get based on the plots here. The solid lines are the non-equilibrium ones, right?
Yeah.
That's one of the equilibrium ones. Could it be that stellar forcing is creating convection in the deeper layers that's pushing you out of the equilibrium as you go to our planets? And you can see that it's getting more and more other than the equilibrium, and you see the lapse rate. I don't know, sorry, not but in general,
I know what you mean, yeah. Almost.
How the methane mixing more actually is decreasing.
Yes. Yes. Yeah. So again, for Zoom, Ravi's mentioning that if you look at the plots here and you think about the stellar forcing, that this could well be indicative of effectively the kind of mixing pushing deeper into the atmosphere. And I think you're 100% correct. I think actually you're connecting the layers more and more as the forcing is getting down deeper and driving those circulations. So yeah, I agree with that point.
Your quenching is also moving up. I think that's what's more internal.
Yeah, exactly. So I know you're going back to India tomorrow, did you say? So maybe we won't have time, but we can maybe talk a bit more. But yeah, I think you're dead right. And it's that balance between almost activating that deeper mixing and that hotter material, and then how far you bring it, and then what the chemistry scale in the upper atmosphere. So what's the time scale of knocking it back again?
Nathan?
Nathan, thanks very much for the discussion, the kinetics, the quenching. It's very instructive to hear about personally, I have a problem with equilibrium chemistry. I study chemistry and it's a little more complicated than that. So I appreciate that. I wanted to ask about your sales pitch about using the different terminators to look at what kind of forces are going on. And I'm wondering if you're going from the one terminator, which I'm assuming is a lot hotter than the colder one, how well would you think that the two will be coupled by going, if your material goes from the hot terminator to the cold terminator, transiting or like traversing essentially the entire cold atmosphere of the planet? Can you still link those two, or what is?
Yeah, so another great question. So yeah, just for Zoom, Vincent was mentioning that point that in my words, sometimes chemistry is the bit that's lacking a lot in astrophysics. Certainly my own chemistry is rubbish. That's why I work with Eric and Maria. It's funny, actually, sorry, just an aside, I said this in Maryland the other day because it occurred to me. Astrophysicists tend to really, really trust radiative transfer, but then really not trust chemistry. But, you know, they still rely on input data. So anyway, So yeah, Vincent's actual question was, how connected are those two terminators if you have this material traversing the whole night side? Yeah, and I think the answer to that is a function of the dynamics and the irradiation, and hopefully by, we can run, or more specifically, Maria can run simulations and make predictions. They're not quantitative, but you can say, oh, well, this might happen, that might happen. Really, I think the observations will tell us, like if, for example, we were able to see SO2 on both terminators for one particular case and not for another, and there was differences in the irradiation. I mean, I'm massively oversimplifying it, but I think that will give us an independent constraint of the dynamics. And the reason that's so important is that direct measurements of the wind that I've measured, those high-res measurements are really expensive, really hard to do, and it's very hard to tie them to a specific pressure level in the atmosphere. So you're sort of, okay, it's telling me the wind, but I don't know kind of where it's telling me the wind. I mean, it doesn't mean they're not useful, not at all. So I think this could be a really good link between that and the chemistry as well.
More questions? Yes, so I have actually two for you. So of course now we have great quality data from wave for hot Jupiter, like it's fantastic. And so people are now they are fitting the data with GCMs, right? And it works pretty well, but of course we have many degeneracies, right? If you use another GCM that you will still fit the data, but you will have a different set of inputs and parameterization. So do you have a feeling of what are we right now doing wrong or not good enough for hot Jupiter GCMs that we need to focus on to better interpret JWST data? Is there like a...
Yeah, there's three components to that. So there's been a big push about resolution. I think increased resolution is great, and you'll know from Earth-like planets, getting more resolution is great, but it isn't a gold standard, ground truth, right? It doesn't matter what resolution you go to. If you know the physics, you can resolve things. But if you look at hot Jupiters, there's magnetic drag, there's a whole bunch of things that you can't just resolve away at the moment. So resolution, high resolution models are really important, but it's not just, oh, we run it high res and then that's the answer. So I think ranges of resolution is more important. Typically, we've done numerical convergence tests, but we've been lazy about them. We sort of run to some resolutions, that's fine. Clouds, of course, more input in clouds, more lab data about condensations of photochemistry is always important. That's not going to go anywhere.
Physics.
Yeah, but laboratory physics, I mean, that's well, that we need loads of that. But honestly, and I'm not saying this just because it's you, I think a hot Jupiter MIP is number one, because you need a way to differentiate a physical uncertainty due to an algorithm from a numerical difference due to a choice. And at the moment, we can run two GCMs, but we don't know if they're disagreeing because we've made a different physically plausible choice, or we've made a different numerical choice that maybe shouldn't have been made or something. So really, until we finish that and get that better, you can have an idea of what the error bars are. So there are two problems, right? There's error bars due to either unknown physics or things in there that are creating problems that we don't, we haven't meant to. And then there's physics we haven't even put in yet. Does that make sense?
Yeah, that makes sense. Yeah. The risk maybe is something, I mean, we were working with Geronimo and Malbec and also with Linda, so on a general protocol paper, right? It's like we may all agree together, but we could still be all wrong together. So the trade-off between accuracy and precision, we can reach a high precision having all those models, but completely being away from the truth.
Agreed, but we're not where Earth models are.
Yeah.
So you need both. Like if we knew, like there's loads of stuff in Earth's climate that's hard to do and that we're learning about, but I think it's probably fair to say that we understand the main drivers. We might not be able to simulate them great, but we kind of understand them. With hot Jupiters, it's a two-pronged attack because we're learning like new chemistry, not new chemistry, but chemistry that's there that, we haven't put in. So you need people, I guess, forging ahead and just chucking stuff into their model. And then you need people carefully coming behind and making sure that we're matching up. And when you combine those two things, we'll get there, but it's going to take time. And that's why, here's my pitch to anyone on a panel: invest in your local modeler now, because otherwise all this data is coming down. You spend billions of dollars on the telescope, and then you'll turn to the theorists and go, what does that mean? And they go, I don't know. So
Thank you. And yeah, very last comment. So what you showed about Mars and the dust, is it like from the or Elfric?
from the
Yeah.
but we're porting it into Elfric right now.
Cool.
So that we want, if anyone's in the Mars community here, I know lots of people do Mars work here. Loads of people in the Mars community got really angry with me because I dared to say, oh, I want to play with Mars, in the UK at least. But what we want to do is create a community model through Elfric. So the is like we're getting that working. That's great.
Yeah.
But with Elfric, we'd like to have a community model for Mars that people can just take away and do what they want with. And I think the rule of thumb is, as you know very well, and the IPCC rules know very well, is 1 or 2 GCMs is not enough. So hopefully it will be a resource that people can use. It's not going to be any more or less right than, say, the PCM from LMD, but it's going to do things in a first principles way. So it'll be like complementary. I think that's the point.
That's great.
If we can get it working.
Do we have any more questions here online?
Nothing in the chat. Too easy. Thank you loads for your time.
All right. Well, again, thank you very much. Let's fix again, Nathan. Yeah. Dear control, yes, I've been recording, so if you still want to watch it again, go ahead. All right, and for people online, yes, see you at the next seminar. Have a good one.
All right.